Recording. We are going to be talking about Lewis structures and how to draw these, and talking about resonance and formal charges today. So, our Lewis structures, of course, they show us how our valence electrons are arranged among our atoms. This helps us reflect the noble gas configuration. And what we're going to use is called the needed available shared method. So the needed available shared. So the electrons needed to make it happy, what is available, and then how many are going to be shared. And that is going to give us the number of bonds in our atom. So you're going to see me writing it like this. Needed available shared. So the first thing you need to know is that there's the duet rule where hydrogen wants to have 2 electrons to make it happy. And then we have our octet rule where we want to have 8 electrons to make it happy, those atoms happy. And then we'll talk later about the exceptions that don't want to have 8. So single covalent bond has 1 pair of electrons being shared, and we draw that with 1 line. A double covalent bond has 2 pairs of electrons being shared, and we will draw that with 2 lines to represent 4 electrons. And a triple bond has 3 lines, which is 6 electrons being shared. So let's go ahead and draw some of these. So the first thing we're going to do is hydrogen. So needed, available, shared. How many is needed for each hydrogen to be happy? 2. Each hydrogen wants 2, so a total of 4. How many are available? 2. So we subtract that and we get 2 electrons are going to be shared. When we share it among 2, so that means we are going to get 1 bond. So then you go in and you draw hydrogen, hydrogen, draw our 1 bond, make sure we have all of our electrons, our 2 electrons, and we do. That's it. So go to fluorine. Needed, available, shared. How many is needed for fluorine to be happy? It's 16. How many are available? 14. So if we subtract that, we get 2. Divide it by 2. That means we have 1 bond.
So you get 14
from the periodic table, yes. So we draw fluorine and fluorine. There's my 1 bond. So that represents 2 of my 14 electrons, and now we need to fill out the octet. So 2. If you do not draw those dots there, I will count off. It's for each fluorine wants 7. The 16 is what's needed. Everybody wants to have 8, except for those exceptions. So the next one, HF, we have our needed, available, shared. How many are needed? Fluorine wants to have 8. Hydrogen wants to have 2 for a total of 10. How many are available? Fluorine comes in with 7. Hydrogen comes in with 1. 8. So that means we are sharing 2 electrons, which means there has to be 1 bond. So then you go and you draw H and F. There's my 1 bond. And then you fill out fluorine to be happy. And there's my 8 electrons. Okay? So let's do the next one. NH3. Needed, available, shared. So nitrogen needs 8. So we need 14. How many is available? 8. So we subtract those. That means we have 6 being shared, divided by 2. So how many bonds will we have? 3.
It's 5. And then you have 3 hydrogens.
So we have our 3 bonds, and we have 6 electrons. So where are our last 2 electrons going to go? On top of the end. They go on the central atom. After everybody's happy, what's left over goes on the central atom. So carbon dioxide. How many is needed? 8 times 3 is 24. How many is available? 16. So we have 8 being shared. Divide that by 2. So we have 4 bonds.
Wait, how is available 16?
Oxygen is, each one is 6 for 12 plus the 4 for carbon. Okay. All right, so now we go and we draw this. Carbon's in the middle. We have oxygen and oxygen, 2 atoms on either side. So we have to have 4 bonds. So how are we going to place those bonds? 2 double bonds. So then we finish out our octets. So that gives me this. What about this? That gives me 4 bonds.
Wrong.
And everybody's happy?
It's non-polar. Should be non-polar, right?
Okay, we're going to talk about this. This is the right configuration too. If you drew this for me,
No, because elements aren't like, compounds aren't like exact.
okay, that's correct too. We're going to talk about resonating structures. That those electrons, they're mobile, so they can move. They can make the double or triple bond. It just depends on what's more favorable. The one that's more favorable here is the one we always see it drawn. That's the favorable structure. And I'm not going to draw CCl4. Let's go and talk about our ions. So let's draw, we're going to draw one for a positive ion and one for a negative. So needed, available, shared. How many is needed here? You determine it just like you would any other one. So we have 16. How many are available? You take how many you have available, and this time we're going to subtract an electron because we need a positive charge. 8. So we're sharing 8. That means we need to have 4 bonds. So we have nitrogen. We have 4 hydrogens, which is good. Each one of those gets a bond. And everybody is happy. And then you need to draw your brackets and do the plus. Available. Electrons available. So let's try nitrate. Needed, available, shared. So how many are needed? 32. How many are available? This time we're going to take available and add 1 because we need an extra electron. 24. So that difference is 8 divided by 2 gives me 4 bonds. So we have nitrogen, oxygen, oxygen, and oxygen. And we have 1, 2, 3, and I need 1 more bond. Where y'all want to put it? Up top right here. And then we fill it out to make everybody have the electrons that they need.
Wait, Amos, wait, I have a question.
Uh-huh.
How do you know the difference of when you have a double bond versus when you're making a molecule lift? Does that make sense?
When you're doing what?
Like, how do we know, like, NH3 is, like, in 8? I mean, I get, like, hydrogens can only have 2, but, like we put the extra electrons at the top of the end. Or is this when we made a double bond?
This one we made a double bond because we know it has that how because it says there's 4 being shared, so that means that we have to have, or 8 being shared, so that means that we have to have 4 bonds. So that's what makes it, we know we have a double bond. And then there's only those certain atoms that can make double bonds.
So the one that was in H3 was, I got it.
Okay, so remember there are those ones that make double bonds, and that is the carbon, nitrogen, oxygen, phosphorus, and sulfur are the only ones that can make double bonds, double or triple bonds. Okay? Anything else? So CNOPs. C, N, O, P, and S. Those are the only ones that will make double or triple bonds with each other. You can't, if you're not part of that group, you're not making a double or triple bond. It's only going to be a single bond. I think in pre-AP I called them my Illuminati. That's that special group that you have to be part of. Okay. So the exceptions. Boron wants to have 6 to be happy. If you go back and remember beryllium wants to have 4 to be happy. Now, if something exceeds, if you have elements that have a D block, so those elements that have a D block available will expand their octet and they will have more than 8 out there. They will have 10 or 12 valence electrons available by just expanding that octet, okay? So we're going to do a couple of these and talk about them. Sometimes the math doesn't work out, and when the math doesn't work out, that's when you know I'm dealing with a special circumstance. I'm probably dealing with an expanded octet, okay? So BF3, needed, available, shared. How many are needed? 30. How many are available? 7 times 3 is 21, plus the 3 from boron. Shared is 6 divided by 2 gives me 3 bonds. So we have boron and our fluorines. 1 bond, 2 bond, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And now everybody's happy. All right. PCl5. I'm going to drop down. Let's do SF6. So needed, available, shared. How many is needed? We have 7 atoms at 8 each. 56. How many are available? 48. That means my difference is 8 divided by 2 gives me 4 bonds. So this is where I'm going to look and I'm going to say something is wrong because we have how many atoms total? We have 6 around that central one. So that means we probably have an expanded octet. So we're going to go sulfur. We're going to put those fluorines out there. We need 6 of them. So 2, 4, 6, 8, 10, 12. And then fill everything else out. And that should give us our 48. Okay, so if the math doesn't work out, then you're dealing with an expanded octet, especially if it's in a third row. So you could this would happen in SF6, but it couldn't happen in OF6 because O doesn't have an expanded octet. It doesn't have a D block because it's in the second row. Third row can have a D block. Okay. So here, let's do some different ones. And C2H4. So how many are needed? $24. How many are available? $12. So we're sharing 6. So that means we're going to have, wait, 12. Oh my gosh. Sorry. 12 divided by 2 gives me 6 bonds. So the one that's in the center is going to be the carbons. And we're going to put a hydrogen on on both carbons.
Hypothetically speaking, if we just like didn't attach hydrogen to one of the carbons, would that be wrong? Like if I did like 4, yeah, it would be, because then it wouldn't,
Yeah. So, and then we do carbon bond, and we have one more. Where does it go? In the middle. And now we're done. Let's go to HCN. Needed, available, shared. How many is needed?
24.
Hydrogen only needs
18.
18. How many are available? So we're sharing. So we have 4 bonds. C is in the middle. Hydrogen can only have 1. So that means the other 3, the triple bond, and we get 2 on nitrogen.
Should we always divide by 2?
Always divided by 2, yes. And then I'm going to go down and do number 20, and then we're going to review real quick. So needed, available, shared for I3, negative. 24, how many are available?
22.
22, because we added 1. So how many are we sharing? 2. So we have 1 bond. And this is where I go, uh-oh, we have 3 atoms here. So we can't have just 1 bond. So we're going to go ahead and draw it out. Put our 2 bonds there. I'm going to make each I on either side happy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to go make the other I happy. 17, 18, 19, 20. I have 2 electrons left over. So where do they go? Anything left over has to go on the central atom. So this is an expanded octet. So there's 5 areas on that I for 1, 2, 3. Yeah, 5 areas for bonding on that I.
So you can just add another bond.
Nope, you can't just add another bond.
Do you have to do the
Because I can't double bond.
Do you have to do the bracket thing?
Yes, thank you. Do the bracket thing. Okay? All right, so review real quick. Remember that C, N, O, and F always have to obey the octet rule. B and BE are exceptions. B will have 6 to be happy, and BE will have 4. Second row elements cannot have expanded octets. And then all the outer atoms have to satisfy the octet rule, and then the remaining goes on to the central atom. So we're going to talk about now formal charge. So what we have here are resonance structures. So a resonance structure is one where there's a double or triple bond, and it's moving. It's not staying on that same atom all the time because electrons are delocalized. They're mobile. So what happens is this electron here, if I'm looking at the very first structure, these electrons here can move and make that a double bond. And then these electrons that here that's making this double bond will move to that O. And when that happens, we get what we see in the next picture. And in the next picture, what we can see happen next is these electrons move back over, and then these electrons will move over and make that double bond. And that's what we get in our next picture. So this is one where this is an overall, the average. So what we see is an average of these. It's going to be hanging around all the time. I mean, that's going to be average. 33% of the time you're going to see this, 33% of the time you're going to see this, 33% of the time you're going to see that. Okay? So let's draw these. If I ask you to draw the available Lewis structures, what structures can be drawn, you have to draw all of them. Okay? Unless I ask you for the most prominent one. So carbon dioxide, we can go oxygen, so doing the needed, available, shared, we can look like that. We can look like this. Or we can look like this. Okay? So all of those are structures. If I say draw the Lewis structures, you would draw all of them. The next one, OCN. If we do our needed, available, shared, then what we will see is we need 4 bonds. So we can have this. We can have this. And we can have this. So those are all structures that we're going to have. And we're going to see that some of these are more dominant than the other, depending on formal charges.
We have to include the brackets in the
Yes, thank you. So include the brackets. I forgot that. Okay. So the next thing we're going to do is talk about formal charge. So formal charge is the charge that will help us look at those Lewis structures that we just drew. They're non-equivalent, and it will tell us which one is the most, the prominent structure. So this, we are going to put a charge. We're going to calculate the charge for every atom. Things you need to remember is that we want to be as close to 0 as possible. Any formal charge that we have should be residing on the most, or any negative should be on the most electronegative atom, which means it's going to be the one closest to fluorine. And to determine your formal charge, you have the number of your valence electrons minus the number of electrons assigned to that atom. So if it has a bond on it, you're going to take half of that. Okay? So if we were to have this here, let's just do the formal charges. How many valence electrons does, let me further draw it out. How many valence electrons does oxygen have? Valence electrons, oxygen, 6. How many electrons are on it? We have the 2 lone, and then we have the 2 from this pair here, so that's a total of 6 is on it. So its overall charge is 0. Carbon has 4 valence electrons, and it has 1, 2, 3, 4 electrons on it, so its formal charge is 0. And then this oxygen over here, again, is 6. Minus the 6 gives me 0. So the overall charge, formal charge, when we take all those formal charges, it has to add up equal to the charge of the atom. So the sum of all the formal charges is equal to the overall charge of the molecule. So the overall charge on carbon dioxide is 0. So when I add all those up, it equals 0. Okay? Everybody good? Let's go do right here. All right, what's the form? We're going to do chlorine. So chlorine has 7 valence electrons. How many valence, or how many electrons does it have on it? 7, so it's a 0. Same thing for the other chlorine. And the other one. All right, what about oxygen? Oxygen has 6 valence electrons. And it has 7 on it, so that is a -1. Now go to phosphorus. Phosphorus has 5 valence electrons, and it has 4 assigned to it, so it is a +1. So the overall charge of this is 0. So let's go take a look at carbon dioxide. Here again are the rules. So we're going to look at carbon dioxide again by giving, we already did this one over here, and we said this was a 0. Oops. This was a 0, this was a 0, and this is a 0. Now if we look at this carbon dioxide here, over to the left, what's the formal charge on the oxygen? 6 minus 5, so it's a +1. Carbon is a 0. Oxygen is on this one is a -1. So which one of these is going to be the most the most prevalent one, the one that we're going to see? Which is favored most? The one with the zeros, okay? And that's why we see it drawn like that, because that's the most favored structure. Now, I'm going to go to the next slide, and you can either redraw what we drew a while ago for the OCN, or you can go back to those other ones and draw those. So, last slide, last structure. I'm going to go to CNO. I have nitrogen, carbon, and oxygen. And this is a resonating structure, so it can also be nitrogen, carbon, oxygen. I'm going to come back with the brackets, yeah. And the other structure that we might see has a triple N and C bond. Okay, so these are 3 structures. We want to know which one is the most favored. So the next thing we're going to do is we're going to go and assign each one a formal charge. So N has a formal charge, if we look at the first atom, has a formal charge of what? -2. Carbon has a 0, and oxygen has a 6 minus 5 +1. All right. So when we add those together, they should equal a -1 charge, because that's the charge on our atom or our molecule, and that's what it is. So now N has a charge of what? -1. Carbon has a 0, and oxygen has a 0. Add all those together, should equal -1, and they do. And the next one, nitrogen has a charge of 0, carbon has a charge of 0, and oxygen has a charge of -1. So now we want to look and say, which one of these is going to be my most stable one? So I would say the very first one where we have that N with that -2, it's really far from 0, so that's going to be the worst because it's really far from 0. So that's our worst one because -2 is far from 0. And then we are left with the next two atoms, and we can choose one or the other. The one we choose, the one that's going to be most stable, is going to be the one that has the negative charge on our most electronegative atom. So N or O, which one's more electronegative? So the O, so this is going to be our most stable configuration. Because the formal charge is on our more electronegative atom. Any questions on that? So I'm not drawing the next one. You can go do that for practice, but that is it. Your homework is C.